Hi, everybody. Last section, we talked about resistors in series and parallel. Again, just a quick reminder about these. For resistors in series, whatever the current is going out of the power source, the current is going to be the same for each one of these resistors. Again, remember the current is not used up. We never create or destroy charge as it moves around the circuit. The thing that is used up is the electrical potential or the voltage as we go around the loop. For resistors in parallel, the current that comes out of the battery here splits up at each of these junctions. Some of it goes this way, some of it goes through this resistor. Then at the next junction, again, it splits up. Some of it goes through, some of it goes into this resistor. And so the current through each one of these resistors is different. And then it adds back up again down here as they all join back up together again. But what's true about this one is the voltage drops across each one is the same. In other words, if you compare the voltages here, they're all going to be the same because they're all connected together by wires, and the voltage here is going to be the same. And so the voltage drops across each one of these resistors has to be identical because they all go from one potential to another potential. Again, quick reminder of how you calculate the equivalent resistance. For in series, you simply add them. And in parallel, you've got to use a little bit more complex equation. All right, let's take now a look at a more complex circuit. We've been talking about resistors in series and parallel, and we've done them one at a time. So in this example, I want you to find the total equivalent resistance of the circuit, the current flowing out of the battery, and the current and the voltage drop across each one of these resistors. First question, are these resistors in series or parallel? The answer is yes, it's both. In fact, if you notice, these two resistors right here are in parallel, and that then is in series with this 2 ohm resistor over here. So how are we going to solve this? We're going to do these two first. Again, for resistors in parallel, the equation looks like this. I only listed the first two terms. Plugging in our numbers, we get 1 over R total is equal to 3 over 6. We have to take the reciprocal of that. And of course, that's 2 ohms. So those two resistors in parallel are equivalent to 2 ohms. Once we know that, we can figure out the total resistance of this circuit. Why? We know these two resistors, which are equivalent to 2 ohms, are in series with the other 2 ohm resistor over here. So we can simply add these together down here at the corner. And here it is, our first answer. The total resistance of this circuit is 4 ohms. Once we know that this whole circuit is 4 ohms, we can actually calculate the current using Ohm's law. Why? We know the electrical potential of this battery right here is 12 volts, and we know the total resistance of our circuit is 4. So plugging those in, we can find that the current in this circuit is 3 amps. And so far you're like, okay, this is not so bad. But now here's where it gets a little bit more complex. We need to figure out the current going through each of these resistors. Well, at this point we know there's 3 amps flowing out of the battery. That's what we just solved. But when it gets to this point, part of the current goes this way and part of the current goes this way. And it doesn't split up equally because these two paths have different resistances. But then over here, the two currents recombine and flow here. And so you're like, wait, this is impossible. We can't solve any of this. Well, think about it for a brief moment. We do know the current through one of these 3 resistors. You're like, wait, no, you just said it splits up. Yeah, we don't know it for the 3 ohm or the 6 ohm. But we know that all 3 amps have to go through this 2 ohm resistor over here. Why? Because it combines back together. And yes, there would be 3 amps of current flowing through over here as well. I just didn't draw it. But all that current goes through there, which means we can calculate the voltage drop across that resistor. If you remember voltage drop, this second equation over here, I times R, we can figure out that the voltage change or voltage drop or potential drop across this resistor is 6 volts. And now we can actually start doing some number crunching. Let me show you. Remember, typically we use the negative terminal of the battery and make that 0 volts. So afterwards it goes through this battery. It's up to 12 volts potential. But we can also then express what the potential is at this point in the circuit. down here, this also has to be 0 volts because it's connected by a wire to that point. And we know the voltage drop across this resistor is 6 volts. And so, believe it or not, we can figure out what the potential was just before this resistor. If it loses 6 volts and gets down to 0, what must be the potential right beforehand? The answer is it must have been 6 volts at that point in the circuit. It loses 6 and it goes down to 0. Now we can actually do some actual calculations. You now know that this point right here is also at 12 volts. This point here in the circuit is also at 6 volts. What's the voltage drop across either one of these resistors? Well, we know the voltage drop across this one has to be 6 volts. It goes from 12 volts to 6 volts. The same thing happens in the one down below. The voltage drop across this one has to be 6 volts. Why? One terminal of it is connected to the 12 volts, the other side to 6 volts. Its drop must be 6 volts that way or 6 volts that way. Well, we know that that is equal to I times R. And if you check your calculations also down, or you can very quickly calculate, and I'll do the same thing over here, you can actually calculate the current for each one of these resistors. We know R. We're solving for I in each case. And you can probably do it very quickly in your head without a calculator, but you'll discover that the current through this resistor has to be 1 amp. That's the I. And the current through this resistor has to be 2 amps. And congratulations, we just solved this circuit. We have the voltage at each point in the circuit, we know the current through each of the resistors, and we've even calculated the voltage drop across each one of the resistors. And so we've got it. All right, let's try another one, this time with all the nice graphics ahead of time. This one, what do we know is true here? Well, in this case, are the resistors in series and parallel? The answer is yes. But these two are in series, and that in turn is in parallel with the 6 ohm. What am I going to do first? Very similar thing to what I did last time. I'm going to group these two together. And for resistors in series, we simply add them. These two together are equivalent to 6 ohms. What's 6 ohms in parallel with 6 ohms? Well, we get 1 over R equivalent is equal to 1 over 6 plus 1 over 6, which you should recognize is 2/6, or basically, it's equal to 2/6, or 1/3. And because we have to take the reciprocal of that to find the equivalent resistance, what's the total resistance of our circuit? The answer is it must be 3 ohms. The moment we've done that, we can calculate the current coming out of the battery. We know the battery voltage is 12 volts. I'm going to leave off units. The total resistance of our circuit is 3 ohms, which means there must be, there must be 4 amps coming out of our battery. 4 amps of current. So there's 4 amps going out this way, and yes, there'd be 4 amps coming back into the battery down below here. I'll draw that in real quick. But the issue is the current's going to split up. Part of it's going to go this way, part of it's going to go this way. And we don't know what part. Now, some of you might actually sort of guess on this one, and you'd probably be right. What fraction goes this way, one fraction goes that way? Well, in this case, it might be easier to look at something else. Again, typically, let's look at the voltages at each point in the circuit. Typically, we make the negative terminal of the battery 0. So it'd be 12 volts here. And because these 2 points are also connected by wires, it would be 12 volts here and 12 volts here. And down below, these 2 points would both be at 0 volts. And you're like, oh, what did that gain us? Well, in this case now, you can actually tell me what the drop in voltage across this resistor is. Well, one lead of it's connected to 12 volts, the other is at 0 volts, means the voltage drop across this resistor must be 12 volts. Well, we know that 12 volts is equal to I times R. In this case, the resistance is 6, and so very quickly you can determine that the current through that resistor must be 2 amps. If you know this is 2 amps, you can actually figure out something very quickly. We've got 2 amps going down this side of the circuit. Remember we had 4 amps coming in. Since current can't be created or destroyed, you know there has to be 2 amps flowing down this side, which means there has to be 2 amps going through, a current of 2 amps through this resistor, and a current of 2 amps through this resistor. Last step, we can figure out the voltage drops. The voltage drop across that top resistor, I times R. I don't know if I even need to write it. I times R, 2 times 4, is going to be 8 volts. And the voltage drop across this bottom resistor, I times R, 1 times 2, is going to be, 2 times 2, I couldn't read my own handwriting, is going to be 4 volts. So the question is, what is the voltage at this point in the circuit? I was at 12 volts up here. I'm losing 8. The potential at this point in the circuit must be 4 volts. And then that 4 volts, I lose 4 more volts, and I'm down to 0. It always has to work out. And so now we've got the current and the voltage across each one of these resistors. And we've solved it. Good. Brain break. We saw it a moment ago. In this case, I just want to show you this one. There are some common letters in these famous trios. So something ing also then shares the letters R-I-T-I-N-G in this next one. And then finally, the last word has R-I-T in it again. Just to give you an example on this one is reading, writing, and arithmetic, the 3 basic ones they used to teach in elementary school long ago. So real quick, I want you to try these. Here are 6 of them. And I would recommend you pause now before I show the answers if you want to give these a try. And here are the answers for those. Shake, rattle, and roll is probably one of the harder ones, along with lions, tigers, and bears. Yeah, and maybe calm, cool, and collected might have been hard. One last one, pause now. And here are the answers for these. These are pretty hard, actually, with very few common letters. All right. Just real quick mentioning this one. We worked with an ammeter in your lab. How did you work with an ammeter? You actually had to remove part of the circuit to stick it in place. The symbol for an ammeter, in your lab, it was actually a small rectangular piece with connections on both sides with a digital display in the middle. But the general symbol for an ammeter is simply a circle with the letter A in it. Ammeters are designed so they have almost no resistance. If you look at the circuit down below here, the resistance is a total resistance of 12 ohms, which means in this circuit, if you use Ohm's law, there should be 1 amp of current flowing around it. Let's say we actually wanted to measure that current. How would we actually do that? Well, we'd actually have to break the circuit. We'd have to cut that wire there and then replace it with an ammeter. And that ammeter should read 1 amp. That's the symbol for it. Ammeters are designed so they have almost no resistance. Their resistance approaches 0 ohms. Think about it for a brief moment. What would happen if this ammeter had some resistance? Well, then the total resistance of the circuit would be more than 12. And the current, when we added it, would suddenly drop to something less than 1 amp. And so typically they're designed to have as small a resistance as possible. In reality, they're never quite 0, but they get really close. In your circuit here, you can sort of see the ammeter here. Yeah, the idea is that the current is unaffected by the addition of this ammeter. Voltmeters. So we've got voltmeters here already. Let's say we actually wanted to measure the potential around each part of the circuit. Up to this point, we've done it always sort of logically. We said, all right, the potential here would be 0. After it goes through the battery, it'd be 12 volts. And then, it'd be 12 volts here. And some of you can very quickly figure out, oh, wait, we'd have a voltage drop. Current's 1 amp. Voltage drop would be 6 volts. It would be 6 volts here. And then back down to 0 volts here. But let's say you actually wanted to measure that. Well, to do that, we would need to add voltmeters along this thing. Something like this. And this would read 6 volts. This would read 6 volts. This would read 12 volts, the potential difference between these points. The key on this one is we don't want to change the current that's flowing through the resistor. We want all the current to go this way, and we don't want any of the current to go through the voltmeter. And that's why they're designed to have almost infinite resistance. So basically the current going through these is almost zero. So it doesn't affect the current through, in this case, the resistor, which is 1 amp. Symbol for voltmeter, just a circle with a V in it. In your lab, it was actually a whole voltmeter, a symbol, or sort of pictorial one of those. Household circuits. Household circuits are interesting. How are the switches hooked up? The answer is they're actually kind of hooked up like this. Again, quick reminder, sorry for a brief moment. I'll just leave that down there. There's usually 3 prongs on each of the wires, and your plugs are actually hooked up in parallel. Each one of these terminals is hooked up to one lead, and each one of these terminals is hooked up to another lead. And then the earth wire is connected, remember this symbol right here, to the earth. And again, remember, we always assume that the earth is at 0 volts potential. The live wire in your circuit is actually, for most of your homes, is 120 volts. The neutral wire is at 0 volts. And one of the questions people always ask is, well, wait a second, why do we actually need 2 things which have a potential of 0 volts? The earth wire literally goes from that plug at the bottom to the earth down below. And yeah, there's a electrical meter over here, your distribution box, circuit breaker box somewhere over here, and then these wires. What's the earth wire for? Well, before we answer that one, let's talk a little bit more what happens. So in your house, as you plug in more appliances, what happens to the total resistance of the circuit? Well, think about it for a brief moment. What happens to the current in the circuit? I'm going to put a battery over here just because it's easier to visualize. What would happen to the current in this circuit if you added more resistors in parallel? Remember, these plugs are in parallel. The total resistance would get smaller and smaller of the entire circuit as you added more things. So what happens to the total resistance of the circuit as you add more appliances? It gets smaller, which means what happens to the total current? Well, total current, again, remember Ohm's law, is equal to voltage over resistance. The voltage of your household circuit remains constant, but as the resistance decreases, denominator gets smaller. What happens to I? I must get bigger. And I actually answered the last question already. The voltage across each of your appliances is going to be the same. They're all at some potential on this side, in your house 120, and over here 0 volts. All of your devices, the voltage stays constant. It's sort of symbolically there. All right. Before I get to the ground wire, I still haven't answered that one. All electrical circuits in your buildings or house or home are protected by fuses or circuit breakers, which actually shut down the electricity if the current exceeds a certain value. This prevents the wires from heating up when carrying too much current. As wires carry more and more current, they get warmer and warmer. If they carry too much current, they get so hot they can actually start fires. In the older versions here, the fuses literally consisted of a small piece of metal which had a low melting point. And so what would happen? This metal right here would actually melt through if too much current went through. You'd actually have to then, if you drew too much current, the wire would melt, it would break the circuit. You'd actually have to unscrew one of these fuses and replace it with a new one. In more modern homes, they use circuit breakers. Circuit breakers, sort of the same idea, look like switches, but if you have too much current, it actually trips. It flips over and turns itself off, in which case you have to then come back over here, push it all the way to the off and back all the way to the on position to re-engage that circuit. Again, the idea here is to limit the amount of current. Most of the circuit breakers or fuses are rated for currents, and typically a circuit breaker is either usually about 15 amps or sometimes 20 amps. Except for extreme circumstances, for example, electric stoves or electric water heaters, which draw large currents, and those might have, and washers and dryers, those would have larger values. Real quick example on this one, and I'm trying to find a calculator. How many 7-watt LED light bulbs can be operated by one of these 15 amp circuits? You can sort of solve it pretty quickly. First of all, we have to figure out how much current one of these bulbs uses. And if you think about this, this is power. And electrical power we haven't looked at for a little bit, but we've got voltage here. We need to figure out how much current each one uses. Well, power, one of the equations, and the one we want to use today, is power is equal to current times voltage. So 7 equals the current times 120. And grabbing calculator, I'm going to grab mine real quick. You can solve, take 7 divided by 120. You can get the current is very tiny, 0.05833 amps. If that's the current drawn by one light bulb, how many of these could you plug in into a circuit that could provide a maximum current of 15 amps? Well, you can take 15 amps divided by how much current each one draws. And if you do that, you'll discover that it's a very small amount of, or very small amount of current for each light bulb, but a large number of light bulbs. You should be able to run 257 bulbs on one electrical circuit. That would be a lot of light. All right. Now, finally, that last piece. So we've talked before about this last terminal here being connected to ground. Why is that there? And also, if you notice, this part of the plug that plugs into the ground is longer than the other leads. Why is it? Well, think about somebody with a drill that only had 2 connections, one to neutral and one to the hot or live 120 volts. What happens if, for example, the wire breaks coming back here to the 0 volt part? Well, somebody grabbing a hold of that metal drill, it now becomes the new path to 0 volts. Because remember, the person's feet are on the ground at 0 volts. Current will actually flow this way. Or in this case, if they're touching a grounded object with the other hand, also would run through their arms one way or another. This is not good because it would run right through their heart. What's the ground lead do? Well, the ground lead is usually connected directly to the metal frame of the appliance. That way, even if there is an electrical short, it's going to flow through the ground wire, which is connected first, back down to the 0 potential instead of through the person operating it. So your washers and dryers, the metal frames of those are always connected to 0 volts. The other thing I want to mention real quick, you'll see these oftentimes in your bathrooms, are ground fault circuit interrupters. What are they measuring? They're very smart devices. They know that if circuits are running normally, the current flowing towards the thing that's plugged in has to equal the current that flows back. But if for some reason you're using a hairdryer or something else, where some of the current, instead of flowing this way, splits up, and some of it flows through you to the ground, suddenly these 2 currents, this one and this one, will not be equal to each other. And the switch compares those 2 currents and says, wait a second, they're not the same, and will automatically shut off the current. These are smart plugs, and they'll notice if any of the current is not flowing directly back. Um, there's usually two buttons on them. One is a test button, usually the red one on top, and the black button down below is a reset button. You should actually test these every so often to make sure they actually work. Um, these are very useful things and they save lives. Brain break, if you want to try it, go ahead and pause now. There's the answers for that one. Common thing in all these is they're all precious or semi-precious stones. In the worksheet, real quick, if you haven't already looked at the key on this one, say you've got 3 appliances and you want to connect it to the power. How should they properly be connected? The answer is always across the entire potential. So the microwave would go like this. The lamp would connect again, one lead to 120 volts, the other one to 0. And your computer the same way. And if you calculate the current for each one of these, the current going through the microwave, if you use, again, power is equal to I times V, the voltage across each one of these is going to be 120 volts. So you'll get 12.5 amps for the 1500 watt object. You'll get a half an amp for the light bulb, which is only 60 watts. And if I can do my math fast enough, 0.833 amps for your computer. So then what's the total current flowing out of the socket? It should be about 13.83 amps. That's probably too many sig figs, but forgive me. Could you run all 3 of these objects on the same circuit, a single 15 amp circuit breaker? The answer is yes. Although if you plugged in a vacuum cleaner in addition, that probably would trip the breaker if it's set for 15 amps. All right. And with that, the last part of this is review. Just mentioning this one, I just want to talk about this one because it confused a lot of students. How do you solve it when you have batteries in parallel? Well, let's say we make this one 0 volts. This is 0 volts. This one would also be 0 volts. And going through either one of these batteries, you would be at 6 volts at this point right here. Doesn't matter which one you go through. Which means this point here is also at 6 volts. If you go through another battery, which increases the potential even more, you'd be at 12 volts here. If you use Ohm's law, I equals V over R, 12 volts over a total resistance of 3 ohms, the current in this circuit is going to be 4 amps. So there'll be 4 amps flowing through this. And now the only tricky part on this one is what happens over here. There'll be 4 amps going through this one as well. But what's the current for each one of these? Each one of these is going to be supplying half of the total 4 amps that's flowing here. Think about it. Current's going to split, join here. And because these are identical, we can cheat a little bit and figure out that each one of these should be 2 amps. Really no math here, really more logic than anything else. With that, good luck on your homework, and we'll talk